Hello everyone. We've been working with linear regression and we've been doing confidence intervals for slopes and hypothesis testing for slopes. But what if our original data isn't linear? How can we achieve linearity? Well, there's two approaches to fit a curve or to straighten the association. And we'll be talking about straightening the association and then looking at the result to see if it's linear and then fitting a model to that straightened association. So one of the ways we could do this is to do a power model. And a power model is in the form y equals a times x to the b power. So notice that we have an exponent here. And if we plot y versus x to the b power, it should be linear. Right now this makes no sense to you, but it will after we look at an example. So here's an example of countries and the income per person and the child mortality rate. This is per 1,000 live births. So you can see Niger here is very high, Uganda is very high, Switzerland has a very low, under 5 mortality rate. And so this information or this data was gathered from a random sample of 14 countries in 2009 from the Gapminder website. And the first thing we're going to do is sketch a scatter plot and describe why it would not be appropriate to compute a least squares regression line. So I have the data here entered into Fathom, and this was the income and the under 5 mortality rate. And so let's graph using income to predict the under 5 mortality rate. And we can see that this is definitely a curved association. It almost looked like a reciprocal function, like 1 over x. So maybe that's what we should try. Let's go back to the notes first to see if we answered the questions. Sketch a scatter plot and describe why it would not be appropriate to compute a least squares regression line. Well, this is what you would sketch, something like this. The income per person in thousands is the explanatory variable, and the under 5 mortality rate in deaths per 1,000 children would be your response variable. So take a moment and do a quick little sketch of this. You don't have to be accurate, but you can sketch that into your notes. All right, the next thing we're going to do is do a power transformation to make the association be linear. And what we're going to do is we're going to do 1 over the income per person. So let's go back to Fathom. I'm going to create a new variable called reciprocal income. I'm going to edit the formula and call it 1 over income per person. There we go. And I'm going to replace income per person with reciprocal of income. And notice that this now appears to be fairly linear. So let's take a look at what we need to do next here. We need to sketch the scatter plot, calculate the equation of the least squares regression line, and make a residual plot. So we have our scatter plot. Here's our scatter plot. And now let's calculate the least squares regression line. So there's our least squares regression line. Our coefficient of determination is 0.92, which is very close to 1, so that's good. Notice this here is in scientific notation. This is about 1.11 times 10 to the 5th times the reciprocal of income, and our y-intercept is 4.6. And let's do a scatter plot of the residuals, just to make sure we have random scatter. And it seems like we have random scatter. However, it looks like the residuals are increasing, so this may not be the best model for us. But let's actually write the equation of this model down. So it was 1.11 times 10 to the 5th. So 1.11 times 10 to the 5th was the slope, and that was times the reciprocal of income, we'd have 1 over income plus the y-intercept, which is 4.6. And over here it says, don't forget the notation for y hat. The y hat would be mortality with a hat. It's very important that you remember to write the hat, because this is just one possible equation. Remember, we had a random sample of 14 countries, and so this is just one sample equation. It's like putting the bar over x when we talk about a sample mean. You need that to show that it's a sample. So this equation is based on our sample of 14. All right, let's move on here. So this was an okay model, but not great because the residuals seem to get bigger. Let's see if there's a better option. Oh, before I do that, let's predict the mortality rate for the United States for the income of a person, an income per person of $41,256. So we have 1.1 times 10 to the 5th times the reciprocal of income, so that's the equation that we need to do for the prediction. So let's do that. So we have 1.11 times 10 to the 5th times the reciprocal of income, so 41,256. And notice there's a reciprocal button here, so I can do it as 1 divided by that, or I can use that reciprocal button, and then plus 4.6. So about 7.29 would be the mortality, under 5 mortality rate in the United States. So how does that compare to the actual mortality rate? Well, remember this was from 2002. I didn't find data from 2002 on the internet, but I found some predicted data from the CIA, and this is also per 1,000 live births. And Afghanistan had the highest infant mortality rate, and the U.S. is somewhere further down here. Let's see. Well, we hope it'd be around 7.6 again. Oh, here we are. 6.17, and that's in 2014. So not too far off in our prediction. 6.17. That was in 2014, so slightly different. It's decreased compared to this, but also this was one particular model. Maybe this particular model is over-predicting for the United States based on some of the data points that we have. All right, let's take a look at another model. We could straighten the data by taking a logarithmic transformation. We could take a log of one or both sets of data, and so what we're going to do here is take the log of both the explanatory and response variables. So let me make this smaller because we don't need to see this whole thing right now. We'll keep it in case we want to do it as a basis of comparison. And let me create some new variables here. We'll have log income, and we'll have log under 5. So this is going to be the log, or you could use natural log, of income per person. And this is going to be the log of under 5 mortality. So let's take a look at a graph of those two variables. Once again, using income, in this case log of income, to predict log of under 5 mortality, infant mortality. And notice this is fairly linear. This is good. Let's take a look at a linear equation for this, so fit a line for this. So here's our least squares line. It has a slightly higher correlation coefficient, which is good. Before our correlation coefficient was 0.92. Let's see if the residual plots are any better. Remember our residual plot when we looked at the reciprocal of income, the residuals got a little bit bigger for higher incomes. We want to make sure there's random scatter and that the residuals aren't getting bigger. Okay, here there seems to be more random scatter, and we have some larger residuals in the middle and some on the end. So this seems to be a better model. So let's write our model down for this. So we'll go back here. So our model would be, let's see, log under 5. So that's the under 5 mortality rate, and don't forget the hat over this. Notation matters. Then we have negative 0.989 times the log of income plus 5.04. Okay. So I would say in terms of the two models that we looked at, this would be the better model because it has a slightly higher correlation coefficient, and also the residuals did not show fanning, which is the increasing of the residuals. Residuals getting progressively larger and larger. So this is definitely a better model. And now let's use this model to predict the child mortality rate for the income per person in the United States being 41,256. So we'd have negative 0.989 times the log of 41,256 plus 5.04, and that's equal to, let's move this over here, that's equal to the log of the under 5. So we need to do this calculation on our calculator, so let's do that. So I would have negative 0.989 times the log of 41,256 plus 5.04. All right, let me write that number down, about 0.475. And here's where you have to remember your logarithms. Remember, a log is basically an exponent, and if we don't have anything here written, we know that this is log base 10. So we're going to transform this to be 10 to the 0.475 power is equal to the under 5 mortality rate. So I'm going to go back to my calculator and say I want to take 10 to this exponent that we have here. So hit second and then the negative button, which gives me the answer, the previous answer to show up on the screen, and I hit enter. So there we have about 2.98, and if you remember 2.98 from this equation, from the website, the CIA website, it was reported that the actual mortality or estimated mortality in 2014 was 6.17. So this model actually underpredicts. But then again, this model is for 2009, and what I found on the website was for 2014, and it was an estimated number. So this is how you can straighten your data and come up with a linear model after you've straightened the data. You will most likely be looking at examples where the data has already been straightened and the equations have already been calculated, and you just need to compare the two models. So the way you compare the two models, once again, is focusing on the residual plot and also the value for r squared. So for example, as I said, these two models, The R-squared value here was 0.93, a little bit higher than 0.92. But the reason why this one was worse is because the residuals got progressively larger and showed a little bit of fanning. So this, in my opinion, would be the better of the two models. So we'll be continuing to work with this when I return to school on Monday, on the 20th. Do the best you can with the homework, and we will, as I said, continue to work with this, and we'll help you out. I hope you have a wonderful weekend.